Okay, let us now look at the exercises. So here's the first one. Exercise 3.2.1. Show that the universal specification axiom, that is axiom 3.8, implies these previous axioms 3.2, 3.3, 3.4, 3.5 and 3.6. Additionally, if we assume that the natural numbers are objects, we also get the seventh axiom. So that means, thus if we permit, this axiom means axiom 3.8, it will simplify the foundations of set theory. Tremendously, because all these axioms are coming as consequences, so we don't even need to mention them. We can work with only this axiom, and if that is the case and can be viewed as an intuitive basis or as a basis for an intuitive theory of sets known as naive set theory, which we have already seen. This is what we saw first of all before before going through axiomatic set theory. Unfortunately, as we have already seen, axiom 3.8 is too good to be true. Why? Because it leads to Russell's paradox. And we have introduced axiom 3.9, the axiom of regularity or the axiom of foundation, to tackle this problem. Exactly how it tackles the problem, we have not got to that. but we will come to that soon. First of all, let us show that the axiom of universal specification implies these axioms. Let P1x be the following property pertaining to any object x, and the property is x is not equal to x. If we have any object x, the property says that it is true if x is not equal to itself, and clearly that is never true. But nevertheless, for this property, according to the axiom of universal specification, there is a corresponding set consisting of those objects that satisfy this property. By axiom 3.8, the following set exists. That's just simply axiom 3.8. And one can verify that this set is nothing but the empty set. So that's how the existence of an empty set follows from axiom 3.8, and that is nothing but axiom 3.2, which postulates that there exists an empty set. So this is over. Next we come to the axiom of pair sets and singleton sets. Let A and B be any objects not necessarily distinct. They may be distinct, or they may be two different names for the same object. Let P2x and P3x be the following properties respectively. P2x is this property. X is equal to A, and P3x is this property. X is equal to A or X is equal to B. Corresponding to each of these properties by axiom 3.8, there is a set by axiom 3.8, the following sets exist. P2x is true and x such that P3x is true. One can verify that the first set is actually the singleton set consisting of the sole element A, that is and the second one is the pair set consisting of A and B. That's how we get the existence of pair sets and singleton sets. So we have now obtained axiom 3.3 as a consequence of the axiom of universal specification. Okay, we are not going to wipe this part, so we work here itself. Next we move to axiom 3.4, the axiom of pairwise union. So for that we must be given two sets. Let A and B be sets, and now we define a property. Let P4 X be this property. X belongs to A or X belongs to B. Keep in mind, I am again saying that whenever we write OR in mathematics without saying anything else, that OR is inclusive OR. That means a statement or another statement means either one of them is true or both are true. If we want to mean exclusive OR, where both cannot be true, we have to do that separately, where we have to mention that but not both. Okay, additionally that has to be mentioned. Here OR is inclusive OR. By axiom 3.8, the set such that set of all objects for which P4 is true exists, and one can see that this set is actually nothing but the union of A and B because of this the definition of the property P4. Although we are just simply mentioning that these sets that we are getting from axiom 3.8 in each case equals the set that we seek, but it has to be proved. Keep that in mind. Okay, we have to actually prove that this is equal to this, no matter how trivial that is. The further we go in proving these axioms, the less trivial it will become. So that's how we have obtained now the fourth axiom, also axiom of pairwise union, as a consequence of the axiom of universal specification. Then we come to the axiom of specification. For that we first need a set. Let A be a set. Let P, okay. Since we already have a property here as in the statement of axiom of specification itself, so let's just call it something else. Let Qx be a property pertaining to any element x in A. That is, for a given element x in A, Qx is either true or false as a statement. Now we define the property that we can use along with axiom 3.8 to conclude something. So let P5x be this property: x belongs to A and Qx is true. Then by the axiom of universal specification, this set exists x such that P5x is true exists, and one can see this set is nothing but the set that we have in the axiom of specification. X belongs to A such that Qx is true. So we have got the axiom of specification also. Now we come to the axiom of replacement. Axiom of replacement is by far the most complicated because it has some conditions in the beginning itself. So let's recall those conditions. Let A be a set for any element x in A and any object y. If you can recall, we take an element from the given set and any object y which may or may not be from the given set. Let Px, y be a property pertaining to x and y such that, now there is a condition, for every x in A there is at most one y, at most one object y for which Px, y is true. This is how the axiom of replacement begins. Now we define our property. Let P5 set, or we can use y also here, but since we already have x and y, we will confuse it with that and we use z itself. Let P5z be the following property pertaining to an object z, and this is the property P5z. P of x, z is true for some x belonging to A. This is my property P. Have I already used P5 before? I can't keep track of these numbers. Here I have used P1, here I have used P2 and P3, here I have used P4, okay, yes, this is P6, Sorry about that. 6 with a problem. Okay. So by Axiom 3.8, this set exists. The set of all objects Z such that P6Z is true. One can verify that this is the set that we want. P6Z is true is actually equal to the set of all objects Y such that Px comma Y is true for some x belonging to A. It's very easy to see why this is so. Just remember that I have already said a while ago that this will become less and less obvious. However, it's very easy to see that these two sets are equal. Just have to look at the definition of P6 set. So that's how we also get the axiom of replacement as a consequence of the axiom of universal specification. And if you assume that natural numbers are objects in set theory, then clearly you also get the axiom 3.7 by defining the property that for a given object Z is a natural number. Then you can get the set of all natural numbers as a consequence of axiom 3.8. Note, however, that axiom 3.7, the axiom of infinity, it does not just say that the collection of all natural numbers is a set. It says more. Actually, it defines natural numbers using Peano's axiom. Okay, and that part we have already seen when we studied or when we constructed the system of natural numbers. There, however, we did not have axiom 3.7 as axiom, but we had it as assumption 2.6. The reason it was only an assumption and not a formal axiom is that at that time we did not have the language of set theory. So we were not able to fully express this assumption formally. And it's the set part that comes as a consequence of axiom 3.8 if this is assumed to be true. So that there this solution ends. So let's now go to the second exercise. It's somewhat straightforward, this one. However, the second one is not that straightforward but more fun. And the second exercise actually gives us a reason for introducing the axiom of regularity. Remember that we have so far not seen any use of the ninth axiom. So now we will see. So here it is. Use the axiom of regularity along with the singleton set axiom to show that if is a set, then A does not contain itself as an element. Okay, we mentioned in the text that this is a consequence of the regularity axiom, and this is the exercise showing that. Furthermore, something else is also true along the same line. If A and B are sets, then either A is not an element of B or B is not an element of A, or both. Okay. Since sets are objects, that is the first axiom. The singleton set axiom implies that the set consisting of this only element, which is the set A, exists. Okay. Now let us recall what the regularity axiom says. It says that if we have a non-empty set B, then there exists at least one element set in B which is either not a set, which is either a primitive object, or if that element is a set, then it is disjoint with B. That's what the regularity axiom says. We now apply that axiom with this in place of B, this singleton set. Because the singleton set is non-empty, so by the regularity axiom, the set has at least one element that is either not a set or is disjoint from A. This singleton set must have such an element, since the only element of this is A, which is a set. We must have this. Okay, so this is the consequence of regularity axiom that allows us to conclude this. Let's see how. In particular, this implies that A is not an element of itself. Why? It's because since A and this singleton set are disjoint and A is an element in this singleton set, A cannot be an element here. That's how we get this conclusion. Next, we want to show that either this is true or this is true. Suppose the negation is true. That is, suppose both A is an element of B and B is an element of A. Okay, let me digress for a moment. If you find it difficult to understand why this is the negation of this, go back to the mathematical logic part and let's just for the time being write it in this form. Negation of A belonging to B, or negation, okay, let me use the logical symbols. Disjunction, okay, negation of B belonging to A. We are saying that this is the negation of this statement. By De Morgan's law from mathematical logic, this is negation of A belonging to B or becomes and negation of B belonging to A. By law of double negation, a double negation of a statement is equivalent to the statement itself. So, A belongs to B and B belongs to A. So that's how this thing and this negation are equivalent, logically equivalent. So that negation we have supposed here, and we will need a contradiction. Okay. By the pair set axiom, which is actually a part of the third axiom, axiom of singleton sets and pair sets. By the pair set axiom, the set consisting of these two sets exists. Okay. Since this is non-empty, the regularity axiom implies what it always implies. This contains at least one element which is either not a set or is disjoint with A. However, A belongs to B intersection A comma B and B belongs to A intersection A comma B. which is a or which contradicts you see, A is an element in A comma B, that is, there is no doubt about that, but A is also an element of B by our supposition. So this is non-empty, this intersection. Similarly, this intersection is also non-empty. So this set has no element which is disjoint with the set. And since the only elements in this set are themselves sets, so the regularity axiom has been contradicted. So our supposition is wrong, that is, we must have either A not an element of B or B not an element